So thank you, Professor Anil Kumar. And first of all, my apologies if that introduction was little longer than required because yeah, it was just a web version. We just picked it from that. So thank you very much. So I am once again Dr. Anil Kumar from CSIR Fourth Paradigm Institute. I am part of the Data Science and Supercomputing Division, and which was earlier institute was earlier focusing on mathematical modeling aspects, but now more of emphasis on data analytics as well. So it is indeed a great pleasure and honor for me to have this opportunity to be part of this event, especially the program being organized as a joint event between ACM and VIT. And also equally excited to see about how many of you? 40, I think, right? 40 plus computer science students pooled from all over the country through a selection process or whatever. So I think what we should do is to make it as interactive as possible, right? Because I think this event has been going on for past 2 weeks. Am I right? Yeah. So you would have already learned quite a bit of stuff, but nevertheless, we would look at some of the very important aspects. So basically the talk is on cybersecurity, which is one of the themes of the workshop as well. But I would focus on some of the very fundamental aspects or pillars like packets, protocols, and attack in cyberspace, correct? You have been hearing a lot about cybersecurity and related things, and quite a bit of jargon words. I mean, lot of buzzwords we would say. But I think what is essential to understand the cybersecurity from a larger perspective is to look at packets, which is the atom of the networking, and then the protocol. Of course, the packets are created by the protocols, and then this combination is actually what is used for launching attacks and all sort of malicious things. So we will look at those things. So if those who are curious on how exactly we are going to spend our next maybe 2 hours or so, this is how my presentation is organized. Would not take too much of time to talk about my own institute, that is CSIR Fourth Paradigm Institute, as well as its cyber security related activities. But we will discuss about the very interesting journey that mankind has traveled from the so-called computer security to the cyber security, right? So, if you go back, say 40 years ago or so, you would not have heard the word cyber security at all. But you would have still heard, I mean, those who were there at that time would have still heard and were concerned about the problem of computer security. But then we moved from the computer security to the so-called network security in between. And now we call the problem as a cyber security. So it has become a very complex global problem that needs global effort and collaboration to tackle it to the extent possible. Even today, I would say, in spite of substantial effort put by global community on dealing with cyber security and cyber attacks, cyber security is a best effort, correct? There's no guarantee for anybody saying that, okay, this computer cannot be hacked or this system is perfectly secure, right? That is because of the way things are developing. Because as and when newer protocols and newer features are launched, you would also see proportionately, they will actually close some of the old vulnerabilities. But at the same time, you also see there are new avenues and vulnerabilities through which fresh attack can be launched. So if you look at, say, 20 years ago and now, many known attacks or many known vulnerabilities are closed, but at the same time, you keep seeing that newer and newer mechanism by which these attacks can be launched. So we will look at some of the fundamentals, because what is required is to know the fundamental of this so that we can have a more solid or more long-lasting solution to the problem. Otherwise, it's become too short, right? I mean, you find out a solution, it stays only for a year or two, and then subsequently you will get a new problem, then you need a new solution, and we get tired of that, right? Yeah. For example, every day your antivirus has to be updated. Not a very simple thing. Somebody tells you that, okay, if you take a vaccination once in a lifetime, you're okay, because you have the confidence on that. But if somebody says it is every year, you will still do. But if it says you need to take a vaccination every day, and still you are not sure whether you will be protected from that or not, and you are going to say, okay, done, enough, right? So that is the level to which, unfortunately, to some extent, the cybersecurity problem is going today. You need to get pull updates every 20 minutes or 30 minutes from a central server, and then update it, then quite a bit of your computer resources like your CPU, memory, and all sort of done is used only for scanning, finding out, and defending. So in fact, it is supposed to be used for more productive aspects like your computation plus data analytics plus whatever. But this become a hindrance in between, which is not allowing you to do it in that smooth manner. So what I wanted to emphasize here is that what is required is a relatively long-lasting solution, if not a permanent solution, which is probably much difficult or because of the nature of the problem. Any of you have questions at any point in time, please stop me. We could make it more interactive. That is the whole idea, right? Then we will, as I said, we'll look at the packets. How many of you, I mean, was there any talk specifically focusing on packets and dealing with that in the last 2 weeks? Okay, you did, yeah, you did. Okay, because a packet level understanding on networking is something very, very crucial, right? Otherwise, we'll be just as we said, we will get vaccination every day, but still we don't have the guarantee that things can be resolved or not. And after I introduce you, I mean, or rather, after as a brush up, we will talk about the packet. Then we will look into the special type of traffic called unsolicited network packets, and also a framework called the darknet, which can be used to capture, analyze, and make inference out of this traffic. So what is special with this traffic is that these are typically packets that is spread across the cyberspace because of certain security events and incidents, right? So that's where I try to slightly differentiate between cyber security and cyberspace security. Of course, the word sounds they are same, but they are quite similar also. But whoever talks about cyber security, what their focus is to protect their resources because they are connected to the cyberspace, right? But whoever talks about the cyberspace security, he is looking a larger perspective, the global cyberspace. The reason is quite clear. If there are lot of malicious devices or possibilities of attacks in the cyberspace, at one point or other, they are likely to reach your doorstep as well. So typically cybersecurity, normally they talk about IDS, intrusion detection system, intrusion prevention system, firewall sort of stuff. All of them focus on your network, which is connected to the internet. But when we talk about the cyberspace, that's why I specifically introduced the word space there. Otherwise, they should probably look more or less the same. Then we look at some of the powerful attacks like massive distributed denial of service attacks and related things, and evolution of these attacks. For example, if you look 20 years ago, I need to move this way. Here, okay, yeah. So if you look about 20 years ago, you would probably see that the attacks were relatively weaker. And in today's scenario, it is quite easy to tackle those sort of things. But then today you have much sophisticated, newer attacks. So we will talk about those things a little bit, and also look at how, when it comes to cyberspace security, how do a malicious guy or an attacker or a network of them try to find out more and more devices or hosts which can be used for exploiting or attacking others. We will also share our own research in this because we have been at CSR 4Pi, we have been working in these areas, and some of the specific aspects. For example, we look at the protocol level interaction between two entities which are involved in a malicious activity. So we also had come out with things like feedback manipulation, flooding attacks and all. So how do we simulate such an attack? How do we visualize such an attack? How do we quantify the impact of an attack? Those sort of things we will discuss. And yeah, if time permits, I would also discuss something called a zero trust architecture, which is a very, very new concept in terms of securing the modern enterprise resources. For example, modern computing environment or an internet environment has become extremely complex. Earlier, it used to be just like, okay, you have a local area network, which is reasonably well defined, and that is connected to the internet. So you know where exactly the connectivity comes in, all right? But today, you cannot even define the border or perimeter. So today's network is becoming more and more perimeterless. If you wanted to put a conventional firewall, where do you put? People don't know, because you have one office here, you have another office, probably, I mean, even if you take VIT as an example, you have another office in Chennai, you have another, this one in Bhopal or wherever. So it is an extremely complex environment. And the devices are also becoming extremely complex. For example, people have bring your own device. All of you would bring your laptop and connect to this network, right? And you take it back, and then you again bring it back. You have IoT devices, all sort of stuff. So what sort of security framework or what sort of security architecture is probably a better choice to secure that sort of environment? So there is an evolving model called zero trust architecture. So you look at the word itself says zero trust architecture, means there is no trust, zero trust, right? The trust level is zero. And what you are talking is that in spite of the trust level is zero, we still need to build a security. But we all know that the trust is essential to build a security, right? Without trust, there is no security. So how do you build security without assuming any trust is the fundamental focus of zero trust architecture. So those who wanted to do more in terms of research or sort of stuff on these things, it would be a very interesting area. So I would also bring those aspects. I would also talk about a program called Spark, Student Program for Advancement of Research Knowledge, which is a flagship training program in our institute, CSR for Paradigm Institute, where students from all over the country can come, join our team and do research on, work jointly. So it's a tripartite collaboration sort of model. Students in the institute, in colleges or universities, we from our institute, and the faculty from this institute as a nucleus of the program, right? So this is our institute, and it mainly focuses on mathematical modeling of complex system and data intensive research. Initially, we were called Center for Mathematical Modeling and Computer Simulation because there was a very strong group and presence in terms of carrying out modeling and simulation related activities. And now we also equally give equal importance and emphasis on data driven research, because data science and a massive amount of data availability. How do we make best sense out of this data in terms of forecast as well as gaining more insight into the system, right? There are two aspects. One is to predict and then see how the future would be based on the existing data. And second is also to look at other aspects from the data in terms of getting more insight into the system which is generating the data. Most of the data is generated by the system, right? Yeah, including whatever data you see on social media, everything. There is a system behind that is driving the data to be generated. So what sort of inference we can do? So most of our activities are powered through high performance computing. We currently have a petaflop scale centralized supercomputing, and flop is a measure of performance of a supercomputer. How many of you have heard about flops? No one? What is the full form? It's floating point operations per second, right? It typically measures the number of floating point operation a computer can do. You can actually measure the floating point operation of all your desktop, but that would be relatively smaller. But in the supercomputing, you actually combine several processors, the capability of several processors, bring them under a single architecture so that the entire system can be used to solve a single problem. So what matters there is the collective performance of the entire system. So we have a system which is of the range of petaflops, which is one of the top supercomputers in the country. I don't remember the exact position in the ranking now. And it is a centralized one. And yet another focus we have is on cybersecurity research and observation. Probably that is why I'm here, to talk to you more about the cybersecurity aspect. So we call this program as CISRO, Cybersecurity Research and Observation. We carry out research to the extent of watching the cyberspace and gain insight from special type of traffics and then see how it could be used for better security inference. So here is a nutshell view of what we do. So we do security analysis of communication protocol, right? Because communication protocol is the one, or its features is the one which is being largely exploited for launching attacks. And we identify possible loopholes or vulnerabilities which can be converted into attack sort of things. Then we also do simulation of attacks, correct? For example, what you see on that right upper side is a simulation of a brute simulation and the visualization from the simulation of a massively distributed brute force flooding denial of service attack, right? Now the advantage of doing why do we do simulation? Why can't we do direct experiment on the real system? Correct. It is relatively difficult to have a system reserved for experiment. But you can still have, but there are more reasons. There are more scientific reasons. For example, if you do a simulation, you get a 100% reproducibility. You are addressing something which you yourself is not sure, right? So at that time, you should be able to do the experiment again and again and get the same result so that you can probably make a conclusion, right? Which is relatively difficult. For example, even if you look at a conventional things, whatever, if you measure the performance between X and Y, two computers, how many packets are transmitted in 1 second? First experiment will give you one number, second experiment is certainly going to give you a different number. They are not going to be exactly the same, right? But if I do run this 10 times, all 10 times will give me exactly the same count, same result, this one. So that will actually remove a lot of uncertainty as you evolve your research. And then subsequently we also conduct a real world experiment, because sometimes what happens is that what you feel from a simulation is an attack, not necessarily reflect in the same form in an experimental platform also. So we also give equal importance to carry out experiment and then look at the means of counter-attack. Countermeasure for dealing with the attack. So this is our cybersecurity research and observation testbed. It's a reasonably sophisticated, purely dedicated for experimentation, okay, facility. Now, what do you expect from an experimental facility? It should have, what are the characteristics if you expect from your lab, your own lab? If you would have done a computer networking labs. A perfect experimental facility, what do you want? Not a production one. Should be reconfigurable, right? One. For example, you do an experiment where you conducted certain things, and your next experiment you may want to set up very quickly without least possible time. You wanted to change the parameters, etc., and then conduct a new set of experiment. Now, how do you change it? You can, one is the physically go, pull this cable, connect it here and this. But that is a relatively old fashion. Now, it is all done through a programmable approach. So actually, this is a facility where you can, to some extent, certain features, you need not even physically go into that room to change it. For example, each of that you see is a node. Okay? So each of that node, I can say that node 1 has to talk to node 2, then node 3, then node 4, then it has to talk to a router, then it has to come to the other side and talk to the receiving side. So I can decide what are the nodes through which the traffic should pass without physically going and changing the cable is one. And I can also say what is the bandwidth at which node 1 should talk to node 2. I could say that node 1 should talk to node 2 at a speed of 100 Mbps. Then I would say node 2 to node 3 should be at a speed of 10 Mbps. So it is called emulation, right? So it allows you to emulate the network. This is different from simulation. Simulation is your single computer you are using and then doing everything. But this is, you have multiple systems, you have the real operating system, you have the real communication protocol running on the system. At the same time, you achieve the desired level of control, right? This is very important, achieving the desired level of control so that you can say, okay, I wanted, for example, A to B communication, I need 10% packet drop. How do you get it? Your production system will never give you. It will try to transmit at the best speed as per the congestion control laws, right? I mean, whatever is the end system A and B, talk at a speed which is equivalent to what the communication system can support. But here I wanted to downgrade it. But those things can be performed here. So that is the beauty of a emulation system compared to a real production system for the experiment. Right? So apart from that, everything is stacked into a single control environment which consists of its own UPS, cooling. So these are called typically smart racks. Now it is available everywhere. But when we set it up, it was one of the unique things. So any questions so far? Nothing. Okay. I think we are ready to get into the core, right? So probably yes, yeah. So some of the simple thing I would probably skip because this is a larger presentation so that we can go to the most important and relevant. So if you look at cybersecurity is being spoken a lot, right? So I would actually congratulate the ACM and VIT team to pick the same topic. I mean, I think we did it once 2016 or 17, but the topic has become more relevant today, right? Because compared to the number of attacks and then exploitation. Even today I saw, morning I was reading a news, there was a alert at a national level saying that critical infrastructure in the country needs to be very carefully secured. There are possibilities of attacks sort of stuff, right? So today we can say that both our personal privacy and national security, two elements, your own privacy, your own this one, as well as the security of the nation, heavily depends on cyberspace, right? A system which did not even exist if you look back something like 40 years ago. And at that time, we were not using the word cyberspace, so it had no impact. And today it has a direct impact on both our national as well as the personal this one. Earlier we used to say a future war could be fought in cyberspace with packet as the primitive weapon. Today I am quite confident we would be 100% correct by dropping the word future war. Yes, wars can indeed be fought on cyberspace and packet could be the weapon, right? This has become a reality. This is really a reality. How many of you know about ransomware? All of you know, right? Obviously. Give me one example. Okay, exactly. WannaCry is one of the most powerful. We will talk about WannaCry and what sort of inference we could do when WannaCry was spreading. WannaCry had two properties, right? What are that? One is that it infects a machine. That is what everybody looked. But WannaCry was also very, very efficient in terms of getting propagated on the network. If one machine is infected and if other guy is vulnerable, he will catch him also and then exploit him also. Then he will, of course, what was it doing? It was encrypting the payload and then asking for ransomware money and all, right? Ransom. Okay. So it's a typical example. You can actually use it. It is a cyber warfare tool or an equipment or whatever you can say, and very, very efficient in terms of this one. So as we said in the previous slide, yes, war could be fought on cyberspace. That is true, and you can have a very huge, you can make a huge impact or a destruction by using that, and packet is a weapon. So let us quickly look at little bit about the packet, right? So packets are generated by communication protocol, everybody knows, right? In your operating system, you have a separate module or it is integrated to the kernel, but it is this particular communication protocol that is making packets. Now, what is the communication protocol we all use today? TCP/IP, right? Yeah, so we'll look at that. But if you look at the packet structure, it typically consists of two portions. You have an header portion and a data or payload portion. So just keep or imagine a letter that you write in your mind. Okay, what happens there? You have address and the content, right? Nobody will write a letter without a content. So the address is equivalent to the header portion, and then what you put inside is equivalent to the data portion. So data typically originate from the person who writes the letter. In this particular case, the person who used the computer. For example, if you are sending an email, that is the trigger from the user side to prepare the data. But the header, who adds the header? Header is added by the communication protocol. Yeah, system, to be precise, within the system, the communication protocol, which is designed as layers, correct? Why are they designed as layers? Yeah, so each layer cannot, see, layer means one on top, right? So a layer, one layer cannot stand without other layer. So they are stacked. Then of course the reason behind this layer is also that communicating data from one computer to other computer in a best effort manner on a network like internet where the packet loss could happen, all sort of scenario could happen, is a complex task. So that needs to be divided it into well-defined subtasks where each of them have boundaries. One will take the service of other end. Okay, so we will see that a little bit more. I know you would have studied it in textbook, but I wanted to give you slightly more or a different perspective from a design point of view. Typically, people say, yeah, I have 7 layers: physical, data link, network, transport, session, presentation, application, right? Yeah, but what do they do? Why do they need? Why are they called layers? Sort of something we will little bit discuss. So it is, header is important, no doubt. Without header, the packet cannot sustain. How many of you have thought about the difference between circuit and packet switched network? Circuit and packet switched network. You know, right? You have a question? Okay, fine, good, yeah. Give me an example for a circuit switched network. Exactly. Telephone network, right? Public switched telephone network. Correct? You pick the phone, dial a number, you can reach anywhere, right? And give an example for packet switched internet. So what is the core difference? Right. I would say the magic is done by packet, right? Now within packet itself, who does the packet switching magic? It is none other than the header. Of course, router does the switching, but for the switching process, what it uses is the header. So a packet switching is a very wonderful invention, and it actually divides the message that you wanted to send to several thousand packets or whatever number according to the MTU, maximum transfer unit, and each packet is sort of intelligent, right? It knows how to go from the source to the destination. For example, out of 1,000 packets, maybe 50 would have gone through this path and remaining would have gone through a different path if that path has a problem sort of stuff, right? Yeah. Now all this switching, reaching it properly the other side, assembling them, everything is being done using the information kept in the header of the packet. So we will see that little more. Yeah. So you already know this TCP/IP protocol suite. That is what is used on the internet. One of the beauties of TCP/IP is that if computer A and B, which is connected to the same switch, talks each other, that also is done using the same protocol. And if you use one computer from here to talk to somebody far off in US, that is also using TCP/IP, right? So the same protocol has a wide range of adaptability. So you all know this is the layered model of communication protocols. I will not talk too much about this, but I wanted to emphasize on this slide little more because this is something very often we miss. So we know we are layers, and we also spoke that each layer is dependent on the other layer. For example, you know the utility ping, PING, very well, right? Yeah, it just sends a 64 byte or whatever size packet to the other side and tries to get a response from that side and then see whether the network is okay and the hosts are up or not. Now, what and all it uses? It, of course, the ping command is typed by the user. Then it starts with the user process. Then it uses a protocol called ICMP. Then it uses IP. Then it uses the network interface card, right? So ping follows this path. For example, you can see it starts from here. Then it comes here. Then it goes to IP. Then it goes to NIC, network interface card. At the same time, if you use another one, say for example, SSH, you know SSH, secure shell. Again, the user initiates it, but that goes here, TCP, and then it goes to IP, then it goes to NIC, and then goes. So it switches through a different modules of the protocol. And if you use what is the other example, DNS, it comes to user level, then it goes to UDP, which is a connectionless protocol, right? That's what I showed. So the TCP, how many protocols are there in the transport layer? TCP, UDP, and so you're slightly outdated. There are new protocols evolving. Of course, most of them will answer TCP and UDP. Even I have shown only TCP and UDP here. But there are quite a bit of, not quite a bit, few number of next generation transport protocols. They are evolving. So we will talk about them. One is called Stream Control Transmission Protocol. Next is called Multi-Path Transmission Control Protocol. Out of that, you would have heard QUIC, right? QUIC? QUIC, QUIC. Okay. QUIC is also another relatively new transport protocol. So this side is getting little expanded. There are more of them. Okay. So you got the concept of how the different layer are dependent on other one, right? Okay. So this is the protocol encapsulation, which is again within the layers. So you have the data coming from the user. Then this old data will go to, this is at this level called a message. You have a header, application header, and then the data goes. The next layer, this old stuff will go into the payload portion, then this layer will add its own header and then it keeps getting propagated, right? So this is called what? Encapsulation, right? Each layer add its header and the data is kept as it is. None of the layer will touch the data, correct? None of the layer needs to touch the data because that is what the end user sends from one side to the other side. But each of them will add header, they also modify header, they also use header, right? And this header is the one which allows the packets to switch through the network. Any question on this design approach? No. So since we spoke about the packet and header, this is the typical TCP packet header. And I don't expect you to by heart it or something, but most of you would probably know this is the IP header. But header looks quite huge, right? Why this much of header? Larger header is better or smaller header is better from a design point of view? Which is better? Logic, simple logic. Smaller, right? Design perspective is smaller. The smaller the header, you can use the remaining portion for your data. The network is to communicate your data, right? Yeah. Your bag alone cannot be 15 kg so that you can put only 5 kg, then the airline will stop you. We don't want that. We want a lighter bag which is strong enough. At the same time, put more of your luggage into that. But then why still this is about 20 bytes, if I remember correctly. Why do we still put this much? This is alone, TCP alone. You have IP again another 20. So 40 bytes. Sometimes what you will be doing is only sending a small hi message. Right? Hi, I am coming tomorrow. So that is maybe 10 characters or 10 into 8, whatever bytes. But your header portion is also quite big. The reason being, in packet switched network, quite a bit of stuff can happen to a packet. You are sending a packet from source to the destination, right? What and all can happen to that packet? Packet can be lost because of what? Why should a packet lose? One is congestion, and is there any other reason for a packet? Data corruption? Yes, yeah. For example, if one bit becomes 0 to 1, somebody can drop that packet in between, right? If your checksum is not intact, the router will drop the packet. So one thing is that packet can be lost either due to congestion or due to corruption. What else can happen? Where is the sound coming from? Right, great, yeah. Sorry, yeah. Yeah, somebody can manipulate it, yeah. But that is more of a malicious or an intervention, right? I'm talking about default packet switched network. You imagine there is no attacker. Correct. Yeah, timeout happens because of what? You lost the packet, right? You send something, you don't get a reply, most probably because that packet is gone, right? That is one of the probable reasons for a timeout. Yeah. But other than, so the basic cause for timeout is actually packet loss. Okay, agree? Yeah. So for the time being, I don't add it as a separate one, but yes, as a good answer, packet can encounter a timeout, which will eventually trigger what? Retransmission, right? If something is lost, what will you do? You have to send it again, right? There is no other option. No magic for an intermediate guy can regenerate something which is lost. So for all those things, for detecting a loss, detecting a corruption, you need, all those things are done using the header portion. Whenever you write a mail, this is something. Do you ever see some portion of the text is missing? No. It always reaches what you write, right? Yeah. So who is doing that? But packet can be lost because IP is a best effort network. So all these things are done by the TCP and IP header. So to complete our previous question where we discussed about packet loss, what else can happen to packets? In a packet switched network. packet can get reordered, right? You send packet 1, 2, 3, 4, 5, 6, 10. What is the guarantee that they all will reach at the other side exactly in the same order? Because something would have gone through this path, something would have gone through other path, and they all are traveling from this side to the other side of the world. So it is touching multiple airports or multiple routers to that matter. So packet can get reordered, right? So, but does it happen if you write an email saying that today is the workshop? Does it become today is the something else? No, it comes exactly as what you. So who is doing that magic again? Exactly. So that is also part of the header. So packet switched network has so many problems. Packet can be lost, packet can be corrupted, packet can be reordered. All these are taken care through design, right? So this is what is the header portion. Okay. And anything else can happen to packet other than that? As he said, intermediate guys can fabricate packets also. But of course, that is not the inherent behavior. But packets can loop in the network. Have you thought about it? It's routing, right? You put a packet on the network, it reached router A sends to B sends to C is supposed to send to the destination, but because of some problem, C again happens to send it to A. So they will keep on rotating. So a packet which you put on the network today, if there is some problem, can stay or keep on rotating in the network forever. Does it happen? What is that field? Time to live. So time to live is designed for what? To take care of that. So we cannot complain that this is too much of header. I think this is TCP header. Oh, so this is IP header. Yeah. So you have a 8-bit time to live header, right? So what is the meaning of that 8-bit? What is the maximum number of? Okay. Correct. So this is a beautiful design choice again, right? But if the distance from A to B is more than 256 hops, what would happen? No, other guy doesn't know. He sent it thinking that it is below 255 hops because it's a 8-bit, right? Maximum you can have is 256 numbers. Am I right? I don't think as of now there is any mechanism to deal with that unless, as you said, probably you need to rewrite it at a particular stage, right? Which is not typically done. What is the need of, what is that? IP header, 4-bit. Yeah, there is a 16-bit header checksum, right? Why it is? Now, why are you worried only about the integrity of the header? Why not? Because we are interested in the whole packet, right?
Because if the header is corrupted, it could lead to the packet going to another destination that's not.
Correct. But why only header is my question. See, I am saying here, you also have a TCP where you have a complete checksum. Am I right? Should be there somewhere. Acknowledgement, this 16-bit. Yeah, 16-bit TCP checksum. That is calculated over the entire packet, right? TCP IP packet. And in addition to that, you have a IP header checksum alone. So who uses which one? In a layered architecture. Any answer from this side? No. See, routing is done by whom? Router. And router wants what? Router takes a decision based on the header information. So his job is to make sure that the header information that he is using is intact and not modified. So he used the checksum portion for that, and then if it is okay, he will send it to the next router. Next router will also do that. Okay. So does a IP router recalculate the header checksum, or he will just check it and then pass it to the other guy? Okay, so something is changing in the header, so it has to recalculate it. That is also another reason why you keep why the designers kept a separate TTL information. Sorry, separate checksum information. So I don't know to what extent I should go for this. So how many of you have generated packets? No one. How many of you have seen a packet? You have seen. How did you see? Through Wireshark, right? Okay. So you run Wireshark on your computer, right? So what traffic you will see? Only traffic that is coming to your network, right? Do you see the entire traffic? No. So if you wanted to do a raw packet capture, of course, this is the typical layout of a traditional computer network where it consists of a number of devices called hubs or switches, right? And which is connected to an internet through a router. Now, yeah, I will skip the previous one. Yeah. See, if you have a hub, what is a hub? It very basically replicate the signal that is received on one port to all other ports, right? It doesn't do any intelligence. So if you have a hub, it is very, very easy to do packet capturing. For example, if you wanted to capture packets that is moving from a bottom left side to the internet, you can have your packet capturing machine located anywhere on the network because it is a hub, so everything will get displayed. But switch is not like that. A switch is a device where the packets are switched using the MAC header information only to the specific place. So if you wanted to do packet capturing in a switched environment, right? For example, whatever the bottom guy is sending to the internet, where do you keep the packet capturing machine? It has to be, so even if it is on this switch, suppose I keep it here, will I be able to capture these packets going from here to the internet? Yeah, because he knows it has to go here, so it knows that it is connected to this port, he will send it here and it goes like that, right? It doesn't come to other guys. So there is a scenario where we have to do a port mirroring. So port mirroring, what you do is that you identify the strategic port. For example, in this particular case, this is the router which is connected to this particular. So every traffic that is going from the LAN to the internet has to pass through this, right? So you mirror the traffic from here to this, and then you connect a traffic capturing machine on that. You would be able to see the entire traffic. Now, once you get a copy of the packets at the network interface level, how do you take it into your user space, which can be analyzed further? So you have two ways. You can use tools like Wireshark, what you mentioned already, command line tools or GUI tools. But the most popular one I would introduce to you is TCP dump. Have you used TCP dump? You have used, because it's a very, very powerful in terms of its filtering capability and various things. But what as a computer science people you should do is that you should capture packets through programming approach, right? So you can write small program which will put your network interface card in a mode called promiscuous mode and capture every packet which can be allowed, which can be used for more detailed analysis. So let us quickly look at TCP dump. So it is one of the most popular command that is used for packet capturing, and it is available on, you can forget about the Linux part now, it is available on most of the Linux machine. You can simply, if you have a root password on your own machine, you would be able to run TCP dump and then put your network interface on promiscuous mode and then capture all those traffic. Oh, this slide is not there. Yeah. So this is how it looks like. So I asked this question, how many of you have seen packets? So this is typically a packet, right, which is captured using TCP dump. So you have the timestamp, time at which the packet is captured. Then you also, what is this? Are you able to read this, or the color combination is little poor? Manageable, right? This is a 48-bit number. So what is that? That is the MAC address, right? This is the IP address. This is the timestamp. Then you have the protocol we spoke already, ICMP, all sort of stuff. So this is a mechanism by which using options you can print the content in an hexadecimal format and all. So my suggestion is that all of you should try TCP dump or a programmatic approach of the same thing and then see what sort of packets are visible on your network. So TCP dump has a very rich collection of options. For example, you just wanted to capture only 10 packets on your network. You can say -C10. It will just capture 10 packets and stop there. You can put the -E flag, which will allow you to decode the MAC address from the packet. It will show the source and destination MAC address. You can put verbose. As you increase the V, you will get more and more details on the packet. So these all are available on the man page or the help page of this one, right? Yeah, here is some interesting thing. Suppose I do a command TCP dump host then an IP address. What would I get? If I simply do TCP dump, it will capture all packets, right? Without any filtering. If you do TCP dump host an IP number, what is it expected to do? Huh? It will capture packets? Right, coming to or fast. So how does it determine that? Yeah, so it looks whether that IP address is appearing in the source or destination part of the packet, right? Eventually everything is packet. So it will compare with each packet, whether the packet source IP address or destination packet is this, then it will do that. And what would you get if you do something like this? I am saying TCP dump, source is this, destination is this, and both source and destination are essentially the same. What would happen? Ideally, you should not see any traffic, right? But if there is somebody still spoofing a number and all, you will still get it. So that is the reason you should try these combinations. Now, all of you know that TCP is a connection-oriented protocol, right? Now, this is the dump of. Okay. So, this is the dump of a TCP connection, right? So, what does a TCP connection establishment do? Sing ACK, and ACK, right? Why is this required? Why do you need these three exchange? We discussed in a packet switched network, packet can be lost, packet can be corrupted, okay, packet can get reordered. So once you establish this connection and agree mutually that these are the set of parameters I am going to use for the purpose of putting my data in the right order. Right order is what? Same order and the same form at which the sender has transmitted it, right? Yeah, so that is, so every data transfer that takes place over TCP has to go through the three-way handshake process. So this is the word. So all of you should run this and then see whether you are able to see three-way handshake on your computer, and you can also try to interpret this. For example, first packet is a sing packet. That is what I put that S in a high color, bold color. Then next is a sing ACK, where you can see there is a sequence number and an acknowledgement number. Then third is an ACK. I know all of you know about connection establishment process, but I wanted to show you the corresponding packet, how it looked like, and how could you try to do this USL. Now, after establishing a connection, what is the next stage? Why are we establishing a connection? To send some data, right? TCP establishes a connection because the user has some data to transmit, right? So this is the dump of a data transfer, which is actually a bidirectional process. What happened? One side sends the data to the other side. What will the other side return? Acknowledgement. So that is also a design choice of packet switched network for connection oriented protocol, that you need to get it acknowledged, then only that packet can be removed from the transmit buffer of the system. Now you established a connection, you transmitted your data, then what is the next step? you terminate it, right? Why do you want to terminate? Because each connection makes use of certain resources in terms of the buffer space, right? Because everything is sits in the memory of the computer. In this particular case, the memory is actually the same as what the kernel uses, right? Right. So you need to finally terminate the connection so that that memory can be used by the next connection. Otherwise, half an hour your computer will hang because it is a server and it has already established probably a million connection and nothing more can be done subsequently. So try out, you do a browsing, parallelly run your TCP dump or Wireshark. I would suggest TCP dump because you can filter it a lot. And TCP dump allow you to interpret, whereas Wireshark does its own interpretation and give you. So it is even better you try with a TCP dump from a protocol analysis point of view. All of you know about IP address spoofing, right? What is that? It is the process of replacing IP address in a packet with a similar looking random 32-bit number, right? That's all it is, IP spoofing. People talk about IP spoofing a lot. It just replaces the 32-bit IP address. So there are two IP addresses, right? What are they in a packet? Source and destination. So which IP address is spoofed normally? Source, right? Why?
If you spoof the destination address, it will go nowhere to an unintended recipe. But spoofing the source will make
But I would say that both source and destination addresses are spoofed. Source IP address is spoofed because of multiple reasons and that is more common. For example, you wanted to hide your identity, right? When you are generating an attack packet and you don't want your actual identity to be revealed, you spoof the packet so that the guy who is receiving it doesn't know where it exactly originated from. For example, a flooding and and by doing that, you also give an illusion to that guy saying that the packets are coming from a large number of hosts. Maybe all of them are actually originating from one guy, right? But he has put all different IP address and gives an impression that what? This is originating from a wide variety of places. So that what would happen? Filtering will become much more difficult. Otherwise, you just identify one IP address and filter the traffic. Now, if I spoof millions of packets, you will end up in spoofing every address. You will end up in filtering every addresses in the internet, and probably that is what the other guy also need. Now, where do you do destination IP address spoofing? Just imagine a scenario where a host is infected by a virus or a worm, to be more precise, and his objective is to spread this to the whole internet as quickly as possible. So one of the ways it can do is what? It will pick the destination address randomly. It is a sort of spoofing, right? He doesn't know whom he is picking. He will generate a 32-bit random number, put it in the destination number and send it across. If that host is up and he is vulnerable, yes, he will get infected. Otherwise, he will not get infected, right? So this is a case where destination IP address spoofing can be used. Yeah, this is that corresponding slide where you replace the destination IP address with a random 32-bit number, and it is typically done by two categories. One is by worm propagation and other one for scanning. You want to scan the internet and find out vulnerable machine. That is also a case where you can do destination IP address spoofing. Now we spoke about protocols a little bit. We spoke about the packets which are generated by the protocol. Now we will look at special type of traffic, right? So far we spoke about the TCP traffic, which is actually expected to be seen on the network by default, right? Now I am going to talk about something called unsolicited packets. What are they? These are packets that you do not normally expect to see on your network, right? Typical example, packets addressed to unused IP address space, okay? For example, you have a IP range assigned to you, which has, say, for example, it's a class B, so you have 65,000 IP addresses. Now, if you are not assigned all these IP address to host, okay, you got the picture? then there is a good number of IP address which is not assigned to anything. Do you get traffic to those IP addresses? Should you get traffic to those IP addresses? No, because you are not using that IP address at all, right? It is like letter coming to a person who is not alive, or it is like you are getting a parcel which you have never subscribed for, right? Yeah. So these are traffic called unsolicited packets. You can also say packets indicating DNS request to a printer. Nobody configure a printer as a DNS server, right? If you still continue to get name resolution request which is coming to a printer, there is something wrong, at least that much you know. Either a misconfiguration or somebody doesn't know but he is still trying to probe and figure out something. Packets addressed to machine which are not up. There are machine, but it was never up due to whatever reason. It was shut down for years together and you have not changed the IP address. But you keep on getting packets to that. But do you get such packets? What is your gut feeling? I think my next slides talk about it. No. Yeah. Yes, the answer is that you really get such traffic. You get traffic to IP address which has not been assigned to any host. You get a traffic to printer asking for DNS, and all of them are actually originating due to malicious activities that is taking place in the cyberspace. For example, worm propagation, reflection of denial of service attack. They have no clue to precisely find out whether my institute is using this particular IP address for a continuous manner. So they do a random spoofing and then do. So yeah. So I already covered this slide. For example, a darknet or a network telescope is a mechanism through which you can capture those packets which are unsolicited. They are also called internet background radiation. Now, by capturing and analyzing this packet, you get a substantial information about the security aspects that is taking place on the internet, right? Yeah. Now, under an ideal condition, you should not get any packet, because that is why it is called internet background radiation. I mean, normally you don't expect it, but you still get it. In real world scenario, you get such packets. So it's a very efficient and effective way to watch the internet and gather cyber intelligence, right? See, your interest is to know what is happening in the cyberspace by sitting at few particular locations, right? You cannot be there on every network, so you cannot find out who is spoofing, who is not spoofing, all sort of stuff. So this has another name called a network telescope, darknet, or internet motion sensor. All of them are more or less similar stuff. So they gather cyber intelligence for better understanding on the potential origin and nature of the cyber threat, and they can also be used for policy decision making. Which part of the internet is generating more of such traffic, so that you can plan for blocking sort of stuff. So globally, if you look at, there are multiple initiatives on darknet or network telescope. This slide is slightly older. If you look now, you might even see more and more large-scale organizations are involved in designing and deploying network telescope or darknet. Some of the typical example is network telescope from CAIDA. CAIDA, I think, is a Center for Applied Internet Data Analysis. It's a good institution in US. They specifically look at internet-related traffic and analyze. There is another one project was there, internet motion sensor and more. And in our own institute, CSIR 4Pi, our team actually design and deploy a small network telescope, which is also very efficient in capturing some of the malicious activities through the so-called internet background radiation. So we already answered this question, whether we really get unsolicited packet. The answer is yes. So if you look at the bottom graph, it is the number of malicious connections that we get on a daily basis. So it is something like, you can see on an average 3 million connections, right? Which is not small. If you look at your production connection versus unsolicited connection, we have seen that the unsolicited connections has exceeded the number of production connection, right? And what is the reason for all this unsolicited connection? Something malicious taking place on the internet, keeping apart a relatively smaller amount of misconfiguration related traffic and all. For example, you can get an unsolicited packet if you ping, and instead of pinging the actual IP address, you made a mistake and that IP address is not there, and somebody is monitoring the traffic, you would treat that also, but that would be a relatively smaller portion. So we already discussed the possible origins of unsolicited packets. One is automated port scanning, where the intention is to find out whether a particular port on the remote machine, so we'll see them quick, okay. But most common reason, one of that is the denial of service attacks that is taking place on the service. So you all know about denial of service, right? Do we need to talk more about it? No, right. So we will skip this, because they are almost as old as the internet itself, right? Because right when we found that internet itself, and there was smaller attempts, but they are not the same. The denial of service attack that you saw 20 years ago and the denial of service attack that you see now, there is a substantial difference in terms of strength or power of the attack. Whatever, it has moved from kbps to mbps to gbps to tbps. I don't know what was the most recent, but I have seen that Mirai triggered attack and all had generated terabits per second of traffic using compromised IoT devices. We all know IoT devices are relatively tiny, right? They don't have huge memory, they don't have huge CPU, right? But attackers had successfully demonstrated that is good enough for me. Give me 1 million vulnerable IoT devices, I can generate terabits per second of traffic. That is what Mirai did, okay? Now, one more problem with these devices is that they are not that greatly well engineered from a protocol point of view. So they have vulnerabilities related to misconfiguration. For example, the Mirai was launched, if I remember correctly, by exploiting default password. Okay, most of these IP cameras had a password, something which was set for by default, and the hacker could just log into that, and his intention was not data. He wanted to use those computers as a launching pad to generate malicious traffic to target somebody else. So the point I wanted to highlight here is that denial of service attacks are old, but at the same time, they are not vanished. They are becoming stronger, more powerful, and more sophisticated as well. The way an attack was launched some time ago and now is largely different. So a very simple example, I mean, those who wanted to visualize it, it is like if thousands of people arrive at a local drug shop asking for bread, right? At some time, it will be very difficult or impossible for a genuine guy to get an aspirin. Because you go in front of a medical shop, you see a huge queue where everybody is asking for something which is not served by that particular person. So unless the packet reaches the router or the end system, it cannot differentiate whether it is good or bad. So that crowd is, so it's a very simple technique, but it proved to be very efficient. So this is what happened. Correct? You can see machines located at various parts of the internet. They run an agent or a botnet or whatever you call, and they all collectively generate the traffic and flood to the target. Now, where is the target? So the target is this link, for example, in this particular case, it's a flooding attack. You fill the pipe here so that no genuine traffic can pass through. So this is called a distributed denial of service attack, which is also getting slightly outdated, and more modern attacks can be launched even much lesser amount of traffic, but can create same impact. So these are the, you will have the slides as well, so I will not go through each of them that deep. But in general, you can look at, if you look at a flooding denial of service attack, there are different generations of them. What does it indicate? The attacker had never given up the idea of launching denial of service attacks, right? They all say, for example, first generation was not effective, so they moved into second generation. Second was not effective, they moved into third generation, fourth generation. And there are futuristic attacks as well, which is much more difficult, if not impossible, to tackle with. So first generation and all is quite simple, as you know, TCP, sync, flood attack and all, where you have only two entities, right? An attacker and a victim. So it is just a one path communication, which exploits the sync flood and all, which I will not go deep. First generation is relatively easy to handle with because you can have sync cookies and those sort of stuff, and you can also have efficient filtering mechanism. Second generation is little more sophisticated. So you can see a word D there. First one was DOS, whereas second generation is DDoS. They are distributed. Okay. So typically consists of multiple attackers or slaves to it and one target. So you can see the structure is something like this. So all of them are typically compromised machine where something vulnerable is running. Was there any talk on DDoS attack in the past? No. It was completely covered. So we can skip. Okay. So the whole point here is that the sophistication on second generation is that you need a set of compromised machine, right? Then you can put your agent there and then do. But suppose you don't get compromised machine. So there are two questions DDoS attack pose. I don't know whether this is discussed or not, probably not. The first question is that are we the target of such an attack, which is really a concern for us because we don't want to be attacked. But the second question is that are we knowingly or unknowingly hosting zombies in our network? Because what happens is the zombies on your network is used to exploit and send traffic to somebody else. Now, in order to succeed with second generation, you need what? You need zombies, right? You need a set of machine which can be compromised where you can. It is not too difficult even today because as I said earlier, you have even IoT devices which has no password or default password. Sufficient of them, you can, an automated program can log into that, put their key and then do the same. But the point is that third generation attack, which does not even need compromised machine. Okay. So the flood actually originates from these machines. These are massively distributed reflection type of attack, where what happens is that these machines are standard machines. They are exploited as a reflector. So you can see here, yeah. You all know every host has to implement TCP three-way handshake, right? Now if you send to a TCP sender a packet where the source IP address is spoofed, what would happen? Normally you send a source IP address is your address, right? But in this particular case, you are spoofed the source IP address. So this man will send the reply or sync ACK to whom? To the spoofed one, right? Because he is seeing that the packet is coming from there. Now the spoofed one has not sent the sync. He has not sent the sync. So he will reply to that appropriately with an RST. Now you imagine 1 million hosts on the internet, all of them getting one spoofed such packet, and where all in that cases the source IP address is the IP address of the victim. It is like all of them together is putting your address and then sending it, and all this RST packet will go to the victim, and that itself is a sufficiently large flood. So that's what it shows. You get a spoofed packet here, where what is the source address in the spoofed packet is this guy's address, and you will send that, then all of them will send a RST packet. So here you have three challenges. In your DDoS attack, you have two challenges. What were there? Are you under attack? Or your resources are used to host a zombie, right? Zombie or a botnet is a more common word used today. But in reflection attack, you have three challenges. The first challenge is same as the first one. Are we the target of such attack? Second is, are we hosting zombies? Third one is, are our end system acting as a reflector, right? This the third one is something very, very difficult to deal with because it is the default functionality of every host or any devices that implement TCP IP. Maybe we'll take a short break now. Is it okay? We'll continue? We will continue. Okay, yeah. So now the third generation attack, what you saw is there is a huge amount of traffic involved, right? Fourth generation attacks are relatively lower rate, means the amount of traffic that you need to generate to cause an attack is much lesser. So what the attacker does is that he generates very tactical patterns which will exploit the features. Somebody spoke here about the timeout, right? Initially when you send a packet, it can get timeout. We said timeout can happen because of congestion or packet loss. But yes, there is a third reason. Timeout can also happen because of a forced attack scenario. Of course, attack scenario also to some extent cause congestion, but the congestion is caused only during this period, right? So what happened? Any traffic a genuine guy send in this period, that also get dropped, because you know router buffer is full here and then it comes down. After some time the packet will get retransmitted, right? Because it has to be sent, it is a connection oriented. If you know when is the packet retransmitted, you will also do at the same time this also. Okay? So you transmitted, you bombarded with a pulse, it got dropped, you did the next one. At that time you know the time, you again did it, you did it. So you keep doing. So the sender will keep sending the same packet again and again. It get dropped each time. And this time you are silent. Now, the second reason for unsolicited packet, because we came to DDoS attack from unsolicited packet, right? The second reason for unsolicited packets observed on the network is large scale port scanning. Port scanning is an event that takes place to find out whether a particular host has an open port with a vulnerable service running on that or not. So this is how it typically happens, right? See, you send a sync request, and if you get a sync ACK from that particular port, what does it mean? That port is open, right? Because he is ready to accept a connection. If you send a sync, you can also get a reply RST, which indicate that 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 port is not open. Okay? Third scenario is today's case is you get a sync, you send a sync, you don't get anything. What would be the reason? Of course, assuming that the host is there, you send a sync, you still don't get a sync ACK. Perfect. It is a firewall. On today's internet, you have a lot of middle boxes. You call it as a firewall, proxy, okay? All of them are configured with large number of security policies. So maybe the firewall is configured, you don't respond to the sync. It's impossible, right? It is your security policy that you have implemented. So that is the third reason, okay? And what you see on the last one is the normal TCP three-way handshake. So three-way handshake is exploited for reflection, and the same way three-way handshake is also used largely for port scanning, and it is still the most commonly used way of scanning internet ports to find out whether something vulnerable service. First is the idea is to find out a port is open or not. Second is to see whether there is a vulnerable service running on that. So why should it trigger unsolicited packets? They scan the entire internet. How many IP addresses are possible in internet? IP version 4? 2 raised to? No. IP version 4 is not 48. 32, right. So how much is that? 2 raised to 32? Quite huge. Okay, it is I think 4 billion or something like that. Now, it is not possible for the attacker to have a list of IP addresses which are active, which are not active. The smallest way he can do is that what? Just generate it randomly and send it across and see a response. So he is scattering, he is scanning traffic across the entire internet, and if you watch a portion of IP address which you are not using, even they will get a port scanning traffic. When I say this IP address not in use, it is IP address which is not assigned to any machine. They are still globally routed and valid numbers. Now coming back to our framework. So this is the network telescope that we have designed at CSIR Fourth Paradigm Institute. So our idea is so the whole idea is that, okay, in internet you have several billion devices. They can be broadly divided into two categories from a security perspective, good machine and bad machine, right? So I use the color red for bad machine and green for good machine. Now the security dynamics is in such a manner that this bad machine has a habit of recruiting more and more machine into their network so that they can be used. Whether it is WannaCry, what is the other thing? Whether it is, have you heard about Lockbit? No. Lockbit is a relatively new ransomware group, RAAS, ransomware as a service, right? So they will come, get into your computer through the propagation model, encrypt your data, ask you money in terms of bitcoins, and it's becoming very, very common. I don't want to name many places, but there are multiple institutions in India and even globally, they all got attacked by this. And they encrypt your data, and they do not only encrypt, what do? They take a copy of your data, and then after certain days, typically I think what was seen so far is 15 days, they will, if you don't pay the ransom, they will put your data publicly open on darknet as a proof. Now if that can be the personal data, for example, an institute will have several thousand students, their biodata, Aadhaar number, this, that, all detailed. So, and if they all get encrypted, they ask money. If money is not paid, in that anger, it gets even published, sort of stuff. So one has to be very careful, sort of stuff. So all of them use a propagation model. This propagation model enables you to get unsolicited packet because they don't know who exactly is their precise target. And that unsolicited packet is what we could use for inference. So I think I already showed this slide. This is the number of malicious connections that we get on a typical small class C network where the IP addresses are not used. So the process we do in a very, very brief manner is sniff the network. So that is what I spoke a lot about packets, because for all these activities, and knowledge at packet level is very crucial or essential. So you sniff, then you get the raw packet from all over the internet, because you will sniff at the most critical location. You now filter the traffic. What is your production traffic? What is your unsolicited traffic? You can use any of those techniques, what I said, DNS request coming to your IP address or a pool of IP address which is not used anywhere. Then you validate the traffic, because you also need to see whether it is subject to an IP address spoofing. So we develop a lightweight active responder, reply to that, and all these things. And if you look at a 1 month period, Jan 1 to 31, we could actually see about, okay, 1, 2, 3, yeah, I think it is 105 million, right? Am I right? Yeah, correct. 105 million source IP address validated connection. That means none of them are spoofed, because we are able to just make sure that the IP address is valid. So this is the way we designed the responder. So these are the packets created by the telescope thing, where we get a sync packet and that IP address is non-existent, but we still capture that packet in between. We will act as if that IP address is alive and send out a appropriate protocol response, establish a connection, and fetch certain additional information. So these are more analysis that you could do using unsolicited packet. For example, you can find out what is the most commonly targeted. So you can see the port number 22 seems to be. What is 22? SSH. So go ahead. Right. SSH and SCP. Both of them use the same port, right? Yeah, very good. So, but you can look at this. Irrespective of the period, I think the A, B, C, D are for 4 different periods. In all those 4 cases, the highest traffic is destinated to port number 22, which is SSH. So, what would be the intention? Yeah, but this machine is not existing. This is unsolicited packet. This is internet background radiation, not your SSH server. He doesn't know it is not existing. He feel it is existing, right? He feel it is existing, so he is doing it, but his eventual intention is to do a brute force password cracking, right? He will be trying various password one after other, hoping that machine is existing. At one stage one can survive, one can succeed in terms of getting the connection. So we look at a wide variety of parameters, which includes the distance, I mean how far it is located with respect to our case. So you can see what at the cumulative distribution in terms of connections. So you can see majority of connections are something like 25 hops away, right? So that is the typical radius of the internet. So now you look at just before the notorious WannaCry got what do you say? I mean got released, right? And it was typically using initially port number 445. And this is the traffic. This was done, I don't have the day, yeah. This was in 2017, I think that in May. That is when the WannaCry was. So how the network telescope in our deployment could watch that. So starting 5, 6, 7, 8 and on, we had a small amount of background radiation, which is of the order of 10K, correct? 10K packets coming to port number 445. Now, when that WannaCry actually got released, we actually got a substantial increase. For example, here you see May 12, 13, how many times it went 10K to 100K. So, you have an extra 0 there, right? It has increased by 1 order of magnitude. So, very effectively we could catch, okay, there is something. Of course, we were not knowing at that time it is WannaCry, and then subsequently it become more vivid that it is this so and so. And after that, we don't get any packet. What is the reason? Is it that WannaCry died all of a sudden? What would be the reason? So you can see a complete silence here, right? Yeah, but do you think the internet would have applied patches that efficiently? Then we would not have been in this position, right? Yeah, but they are infected. Once a machine is infected, they could switch into a different port, but whatever was infected would have already been there, right? It's a complete silence. I get 0 packets. There was a collective effort by multiple internet service providers to realize and react to this scenario. So port number were blocked. Router or intermediate devices, at least at a regional and national scale, decided that okay, for some time we will not respect, because it is much better than having more and more machine getting infected by this ransomware, right? So there is this one, and you can see a smaller portion here, because for a short time our service provider, again for an experimental purpose to measure, they again opened that port. Then we could see that okay, again they are trying to pick up. But the most important point is that the start was on May 12, 2017, around sort of 12, okay, this would be 1 o'clock, I think, 1 in the noon sort of stuff. That is when, according to our observation, this is a smaller telescope, so a larger one would have given a better one. So you look at this. This was when, much before the WannaCry started spreading, I think. Yeah. No, this is, I think, after applying the kill switch. So WannaCry had a kill switch. You know about it? Okay, I think you should read about it on the internet. What is it? Basically, it actually had a, yeah. If you look at this domain name, can you really have a domain name of that nature?
Somebody bought the domain name and initiated the switch.
Yes. So this was built into the code of WannaCry. What it is supposed to do is to first try for a name resolution. If it is there, then you do this. Okay. Now, if this is true, then WannaCry doesn't get, it doesn't propagate further. So this was acting as a kill switch to stop the worldwide spreading.